right. Hey, everybody. We're going to go ahead and get started. Let's see. Great. So, the material does move fast. One nice thing about that is if you ever don't like a topic, we're on to the next one pretty soon. So we're done with graphs for now. Not on your homework. There's still some graphs to do on the homework. But we're on to a whole new topic now. It's one of my favorites. I don't think we'll spend as much time as I would like to explore all the concepts. But yeah, I love this topic. So warm-up question to start with. It's Thursday, and a friend has to meet in 37 days. What day of the week will that be? All right, so we don't, we're not asking about like what calendar day it is, like the 19th or whatever, just what day of the week, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, or Sunday. So starts on Thursday. That's when the friend says, let's meet in 37 days. What day of the week will it be? Anyone have any thoughts? Yeah. Saturday. So we have a guess for Saturday. Who else thinks Saturday? Okay, great. Can someone tell me where they're getting Saturday from? Yeah.
Because meet in 37 days is just like meeting 2 days, because 35 plus 2 equals 37, and 35 is like 5 weeks.
Great. Exactly. 37 can be broken up into 7 times 5, which is 35, plus 2. And we really care about that too, because what's special about this right here, why did we break it up into sevens? It was said by, it was just said, but why are we breaking that up into sevens? Yeah. These are all Thursdays, right? Every 7 days it's going to be Thursday. The week wraps around. That's just how we keep track of days. The week wraps around, so every 7 days it's going to be another Thursday. So, 7 days, it'll be Thursday. 7 days after that, it'll be Thursday. Each of those 5 times, it's going to be Thursday. And then all we care about is 2 days after that, which is Friday, Saturday. So this kind of represents Saturday. Thursday, 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 Friday, Saturday. Right. So what if they said, instead of 37, 50? What if they said 50 days instead? Anyone have a guess for what day it'd be? Yeah. Yep. So we have a guess there. For this one, it'd be Friday. And same reasoning, right? We have 50 is equal to 7 times 7, which is 49, plus 1. Great. Last little question is, what if we go back to saying 37 days? They said 37. And then right before the day ends, they say, actually, that doesn't work for me. Can we push it back 5 days? Go 5 days forward? Any guesses for what it would be there? Yeah.
Thursday.
Be back to Thursday again. Why? Because we get to 42. And 42 is a multiple of 7. So really, you might as well have said 0 days in terms of what day of the week it'll be. So this is a weird thing, right? 37 plus 5 equals 0. Math gets a little bit weird when we get into undergrad. But really, we're not saying we're equal. We're saying something is equal with 3 lines mod 7. So we need some new definitions. Right? We're going to need some new definitions, but we have the intuition. And it's basically that, I'll erase this, yeah. Yeah, I'll erase all this. It's basically that we're used to the number line being this straight line. Right before we get this definition here, we're used to a number line being this big old straight line where we start, maybe we have 0 here, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and we can just keep going. 12. Actually wanted to write more, but that's fine. So we're used to being the number line going on forever. But the point is, if we're asking something like, what's 2 plus 6 mod 7? Now, we haven't defined what mod is yet. But we kind of have some intuition already. So 2 plus 6 would be 8. But 8 mod 7, we're asking about the remainder, right? So 8 mod 7 is going to be 1. Why? Because 8 is equal to 7 times 1 plus 1. There's the remainder. So really, 8 is the same thing as 1 here. If we're looking at what the remainders are, 7 is going to be what?
0.
Then we get 1, then this is 2, 3, 4, 5. Right. So really, we're getting kind of, if we went out to 15 here, 15 would also be the same as 1. So instead of thinking of a number line, when we're thinking about modular arithmetic, that's going to be what the lesson is today. Really what we're dealing with is a circle. 0, 1, 2, 3, 4, 5, 6. Because each time we get to 7, we just kind of wrap right back around. So modular arithmetic often is talked about like arithmetic on the clock. And we're kind of used to this, right? Because this is how we tell time for the most part. So, I have my phone in military time. I have most of my clocks in military time. Traveling a lot as a grad student was much easier to just kind of do the math if I had military time. So if I say it's 14 o'clock, what would that mean for AM, PM folks? It'd be 2 p.m., right? So 14 o'clock is the same as 2 p.m. Why? Because the PMs is a circle around 12, and this is a circle around 24. So 14 mod 12 just means, yeah, we get to 12, and then we go to 13 and 14, but we don't have that on the clock. We have 1 and 2. All right. So we're just doing arithmetic like we used to, except in a circle. All right, so let's look at a few things. 2 plus 6 is 8. One way to look at that is if we're starting at 2, instead of counting up the number line here until we get to 8, we could just count around 1, 2, 3, 4, 5, 6, and we get to 1. So I'm going to erase this line real quick. And one thing to say is 8 is kind of the same as 1 when we're talking about around the clock. What's, another number that's the same as 1? Mod 7. We're doing around the clock mod 7.
15.
15? Yeah, because 7 times 2 is 14 with a remainder of 1 to be 15. Another one?
71.
71, perfect. All right. And we could keep going. But there's a whole bunch of numbers that are the same thing as 1 because they have the same remainder as 1. That is, when you divide these by 7, they have all a remainder of 1. So yeah, we can do addition. We could do 2 plus 6. What about something like 4 times 5? Yeah, 4 times 5, first off, we know what that is. That's 20. But what is that mod 7?
6.
What is that, 6? Yeah, ooh, yeah, 14. Because 20, we can always write it out, is 7 times 2, which is 14, plus 6. So this is really 3 equal signs to 6. I can't cross this part. Let me just rewrite this a little bit. 4 times 5 is equal to 20, which is congruent, we'll say what that means in a second, to 6 mod 7. All right. So one thing we could say here is 20 is the same as this over here. In the same way, we were kind of like seeing all these things that are the same as 1. 20 would go over here. And real quick, 79. Just think about 79 for a moment. Show me on your fingers where 79 would go on this clock. Sing lots of 2s. Right, yeah. So 79 would go here. You know, you have to do multiplication a little fast in your head, but we know 79 is equal to 7 times 11, 77 plus 2. OK. So we can kind of have a sense of adding and multiplying around a clock, but let's get some definitions on the board. Yeah?
Just to clarify, that's for mod 7, right? So
Yeah.
if you have any mod, there will be a remainder up to -1 of that number. So will your clock kind of be up to n -1?
Yeah, so more generally, and we're about to give like a formal definition, but more generally, if we have mod n, that is, we're dividing by n and looking at remainders, that is certainly going to be 0, 1, 2, all the way around until we get to n minus 1. So you can have any size clock you want. Right. So some definitions. It's nice to have intuitions, but it's really nice to have definitions when you're trying to prove something. So we're going to say that A is congruent to B mod n. This equal symbol except 3 of them, that's called congruent. I don't know the history of that. It just A is congruent to B mod n. If and only if, that is, it's a definition, there exists k, j, and r in the integers such that A is equal to k times n plus r. That is, A is a multiple of n except with the remainder of r. And B is a multiple of n plus r. The big important part is that these are the same remainders. All right. Ooh. So this is basically kind of what we were intuitively saying, right? We're saying that 2 things are on the same place in the clock if they have the same remainders with respect to n when you try to divide by n. Yeah? Sorry, can you say that again?
So you have A is equal to B mod n.
Mm-hmm.
A mod n is equal to B mod n.
Ooh, good question. So this is a little definitional, as in the mod n is off to the side right now. We'll talk about moving the mod n throughout equations later, but right now we're just saying another way to say this, and you'll see this in the notes as well, is A congruent with a little subscript of n there, B. Let me draw that a little bigger. An equivalent way to say this, it's just notation, is A is congruent to B. So putting the mod n to the side right here is just notation. And it's saying that, yeah, A is congruent to B with respect to n. And that's the same thing as saying A and B are congruent with respect to n. Another definition you could say here, these are if and only if, so these are all equivalent definitions, is that n divides A minus B. So you could have this definition, I'll draw a box around it, or this definition, and they mean the same thing. And just taking a little look at this, this is really saying, kind of subtracting on both sides here, right? It's just saying that A minus B is congruent to 0. Ran out of room there. Mod n. Which is to say, A minus B congruent to 0 mod n just says n divides A minus B. Right? No remainder. That's what 0 means. There's no remainder. So these are definitions. We need to play with them a little bit to get intuition for them. This one should look the most familiar with what we've seen so far, is just two things are congruent if they share a remainder. Which is why when we said, what was it? How many days did we say? 37? Yeah, 37 days. When I said 37 days, someone responded, well, that's basically 2 when we're considering mod 7. We didn't have the language mod 7 yet, but it's saying it's basically 2 because they have the same remainder. So if all we care about is days of the week, we don't really care about a whole number line. We're just going to loop. We can say these are basically the same, and we'll see really what that means in a moment. Yeah? Can we have B be negative? Great question. We'll get to that in a moment, and I'll take that question too.
What are you trying to prove with the A minus B in the second box below? Yeah. What does that do? Like showing that A minus B is divisible by n. Like, what does that show?
What does this show? Yeah, let's write out that for a second. So which one do I want to do first? I'll write out what this means, and then we'll look at negative numbers. So first, what does n divides A minus B mean? It means n divides A minus B, which, by definition, just means A minus B is a multiple of n. That is, there exists k in Z such that A minus B is equal to n times k. So that means when you subtract B from A, you get an exact multiple of n. Another way to say that is that if you look at A, the remainder it has is B. We're talking real general definitions right now, so I think we should start looking at some examples. Was there something specifically you were asking about what this means? Because we can kind of mess around with definitions.
I just don't understand how those two boxes are showing the same thing.
I see. Got it. OK. Good question. So the question is, why does this mean this? So to do that, we'd have to do an if and only if. Right? We'd have to show that this implies this and this implies this. OK. Real quick, if we wanted to show this implies this, what's A minus B here? If we subtract A and B, what happens to the R's? They cancel out, right? So now we have some, if we subtract A and B, we get a multiple of n, and the R's cancel out, which means A minus B is congruent to 0. Right? So that's real hand-wavy, but that's how this proof would go. If we wanted to go from here to here, we know A and B are of this form. If we do A minus B, the remainders cancel, so now A minus B has no remainder. Yeah?
So does this mean that all even numbers are the same?
Depends on what your clock is.
Like, are they all the same mod 2?
Mod 2, all the even numbers would be the same. Exactly.
So would all the odd numbers?
So would all the odd numbers. So yeah, let's start looking at some examples. Yeah?
One question regarding the definition that
Mm-hmm.
for modulo. Say that B is equal to J and plus R. So does that imply that B could be, for example, greater than n? For example, if J is equal to 1, does that mean that you could write the sentence that like n is equal to 7 mod 3?
Yeah, let's just look exactly at that example. So let's say B is equal to what? You said 10?
Say that B is 7.
7, OK. And what's our mod? 3, OK. So what's something that is equal to 7 mod 3? Another number. 1. OK, so 7 is equal to 2 times 3 plus 1. So 7 mod 3 is equal to 1. 7, when you divide by 3, leaves a remainder of 1. Right. So now the question is, if we want to say 1 is congruent to 7 mod 3, here's a b that's bigger than the modulus. Here's some other a. And yeah, so what we have is that 7 does have this form. Here's a is equal to n times something plus a remainder. And 1, well, what's that equal to? That's 7 times 0 plus 1. So here's an example. Yeah?
So does either A or B have to be within like 0 to n minus 1, or can they both be like
A and B can be anything you want. So let's look at a few more examples. Yeah. Yeah. Let's get back to the negative number question. So once again, we can look at the number line. We get, we have 0 here, 1, 2, 3, 4, 5, 6, 7, 8, 9. And if we're doing mod 7, then we start repeating again, right? 8 is the same as 1, 9 is the same as 2, and so on. What happens if we get negative numbers? What happens if we get negative numbers? What's negative 4 plus 2 mod 7? So we can do it kind of, let's see. Negative 4 plus 2 is what? Negative 2? And now the question is, what's negative 2 mod 7? Kind of a weird question. So I think we need to really think about what negative numbers mean. So if we go backwards here, there's a few ways we could look at this. We're going to look at it a different way later in class, as in later today. But one way we could look at this, we get 0, 1, 2, 3, 4, 5, 6, 7. Oh, sorry, that actually should have been right here. 0, 1, 2, 3, 4, 5, 6. 0, 1, 2, 3, 4, 5, 6. 0, 1, 2, 3, 4, 5, 6. We'll just keep spinning around that clock. What happens if we go backwards on this clock? So negative 2 goes back 1, 2, and we're at 5. Right. So we can look at this the same as everything. We get 6. I feel like I want a different color for this. Zero, 1, 2, 3, that goes on. And we have 0, 1, 2, 3, 4, 5, 6. And again, we have 6, 5, 4. That's not the best marker. I think that's the only color we have. OK. But the point being 6, 5, 4, 3, 2, so on. So these are good questions about like what negative is. We can think of negative 2 as 5, but we haven't really been convinced why. So let's look at a few examples and see if we can start seeing some patterns from there. Yeah, so let's just start seeing some patterns. So we have these definitions. They're not the most revealing. There's some intuition that things should have the same remainder. And we kind of hand-waved about how we would get from here to here. Why they're saying the same thing is that if they share a remainder, then their difference should be 0, as in their remainder should cancel out. But, you know, we've kind of seen one example right there with b equals 7, n equals 3. But if we say n is congruent to 15 mod 7, one definition we have is that, well, what's 8? 8 is equal to 7 times 1 plus 1. And 15, we have to break that up, but what better be true is that it should have the same remainder. if 8 and 15 are truly congruent mod 7, they should have the same remainder. And in fact, they do, because 7 times 2 is 14 plus 1. So that kind of like sanity checks our definitions here. Yeah?
Just from the previous example, you did the addition first and then the mod. Like, what is the order of operations?
Great question. OK. So we're getting to all of this. That's a great question. And there's a question here.
Yeah, wait, is 2 mod 7 2?
Is 2 mod 7 2? Yeah.
And then is negative 2 mod 7 5?
Yes. OK, so 2 is congruent to itself, mod 2. 1 is because it's equal to, what would I need to multiply by 7 here? 0 plus 2. Integer, integer, it's all good. And now this question of negative 2 congruent to 7 is 5. Where does that come from? Well, what we want is there's a remainder of 5. What do we need to multiply 7 by here? Right. Negative 1 sure is an integer. 7 times negative 1 is negative 7 plus 5 is negative 2. Yeah?
So why can't we do 7 times 0 plus negative 2?
7 times 0 plus negative 2. You can, certainly. So, right. For 8 and 15, for example, we're all looking at the smallest positive number here. But you certainly could write this so that there's an 8 here, or a 15 here, or a 71 here. We didn't specify that there's only one remainder. There can be a whole bunch of remainders. Yeah, let's look at some examples. Because I think looking at the definitions begs more questions than it asks. Yeah? What would it mean if you modded by a negative number? Oh, I see. Where n is a negative number. I don't think we have a definition for that. You could talk about it in terms of division as well, but I don't think we typically talk about that. We're typically talking about positive numbers that we're modding by. Yeah.
Does n have to be an integer?
Yes, n has to be an integer. Yeah, we're working with discrete math here. N does have to be an integer. So before we dig more into definitions, I'm just going to give you a bunch of problems, and we're going to solve them to make more sense of this. So I think we're getting a sense of how to just do it, even if we don't know the definitions and why they work and the sort yet. So 8 plus 9, we know that 8 plus 9 is always 17. But mod 15, what would that be?
2.
Yeah, 2. OK, so we get this hang of it. 4 times 3. And let's do mod 7. Yeah, I'm hearing 5. Why? Because 4 times 3 is 12. Mod 7 is 5. 7 goes into 12 once with a remainder of 5. If I'm trying to solve for x plus 3, x plus 3 is congruent to 5 when we're dealing with mod 7. What do I add to 3 to get 5? Well, in this case, it's not much different than usual. We can just say it's 2. Oops. 2. 2 plus 3 is 5. And then really what we're getting at here, yeah, let's go ahead and just go into this. All right, so let's go into some harder examples. We're getting the idea of just how to do basic, just multiplying things, look at the remainder. Let's look at something a little bit trickier. First, start easy. And then I'm going to ask some trickier ones. 57 times 26. And 5 to the 58 mod 7. Okay. First one, not too bad. 7 times 3 is 21. Mod 9 is 3. Yep. 9 goes into 21 2 times, which is 18. And then there's a remainder of 3 to get to 21. 57 times 26 is, I don't want to do that. Right? No one wants to do this. No one wants to multiply 57 by 26. We could do 57 by 26, but I was already hearing some people ask some questions about there maybe's another way. If you had your dreams come true, what way would you like to solve this? Bit of a vague question, but some people were already asking about basically this idea here. Any thoughts? Yeah. Yeah, so I'm hearing, so I've heard the same thought, which is instead of doing 57 times 26 and then mod 8, because 57 times 26, that sounds awful. What if we do 57 mod 8 times 26 mod 8? Like, if we simplify this and then simplify this, it'd be much smaller, nicer numbers to work with. But there's a question of, can we do that? How do we know we can do that? So what I'm hearing then is a conjecture. So let's write a conjecture here. Conjecture. If A and B are congruent, and C and D are congruent, really what I want to say is then, for this problem here, it'd sure be nice if instead of A times C, we could replace A with, we could replace A with B. Because A and B are the same, what if we can just swap those out? Does this statement make sense? If A and B are the same, mod n, that is, they're congruent, and if C and D are the same, mod n, then instead of doing A times C, you can just swap other things that are the same out. That is, instead of A, put B in, instead of C, put D in. We need to prove this. If this was true, what's another thing we'd want to be true? As in, if we had multiplication where we can just swap things out, we also might really love, exactly, if it was also true for addition. So let's just go ahead and prove these. Yeah, let's go ahead and prove these. So let's do, proof of 1 first. Right? So direct proof. Here's our antecedent. So just assume A is congruent to B and C is congruent to D. Well, what can we do from there? The nice thing is we have definitions, right? We're no longer in intuition land, we're in definition land, so we can just start writing out what's true. Let's go ahead and choose this one. If it doesn't work, we could choose another. But let's go ahead and choose this definition. This means that n divides A minus B, and n divides C minus D. That's just the definition of what this notation means in the first place. Right. So n divides both of these. What that means is that there exists k and j in the integers such that, let's see, a minus b is a multiple of n. That means a minus b is equal to n times k, and c minus d is equal to n times j. Great. All we're doing is following our pencil. Right? And if you ever, especially with modular arithmetic, we're back in numbers again. Especially in modular arithmetic, if you're ever stuck, try just writing down the definitions of the antecedent and see if you can just follow your pencil. That's all we've done so far. So if we're trying to prove 1, with these definitions, what can we do from here? We just try things at this point. There's no one right way. So we can try adding these two things because we want a plus c at some point. So I could do a minus b plus c minus d, and that's equal to nk plus nj. It's looking a little better. But if we ever get stuck, like if you ever like, OK, I'm writing a definition, everything seems to be following, and you ever aren't sure, oh, I didn't want to erase those. That's fine. If you ever get stuck, just remember to write out what we wanted to show from the beginning. This isn't part of the proof, but it can help guide you where you want to go. So what did we want to show? We wanted to show that a plus c is congruent to b plus d. And we could stop there, but if we're here, that doesn't tell us exactly, that doesn't help us that much. So again, we can, without making this part of the proof, we can say, well, this means that n divides this definition. That is this minus this. A plus c minus b plus d. Is this clear here, right? This is just the definition of what this means. It says n divides this minus this, which is how we defined it over here, a minus b. So this side, once we write it out this much, might give us a little bit more clue of what we want to do here, which is we can just group terms, and we're basically done. If we group a and c, the positive terms, minus, and then group the negative terms, b plus d, that's equal to, we can factor an n out, and we got k plus j. Why are we done? Yeah.
Well, if we're looking at a mod n b, then a minus b is equal to n is what we get from that. If we're doing a plus c is mod n is b plus d, then we can just do the left-hand side minus the right-hand side divisible by n.
Right. So we've basically have this thing right here looking exactly like this. Just about. We just need to argue that this side is a multiple of n. And it is because k plus j right here is in the integers. All right. K and j were integers, so k plus j is an integer. And now what we have is that a plus c minus b plus d is a multiple of n. And that's exactly what this was. So we can write it out to say that what this means is that n divides this. And what that means is that a plus c is congruent to b plus d. Any questions on this proof? We're just kind of proving what this implies this. All right. Let's go ahead and prove 2 real quick. And then we're really off to the races, because these are powerful here. 2. Let's prove 2. Again, let's start the same. In fact, is everyone OK if I erase this? Anyone want this up still? OK, I'm going to erase this. Because we're starting exactly the same. Right? Proof of 2 has the same antecedent. We're assuming A is congruent to n. A is congruent to B mod n, and C is congruent to D. And I erased too much even, because that means that, n divides A minus B, and n divides C minus D. And again, we know what that means. That means there's a k and j in the integers, such that A minus B is equal to n to the n times k, and C minus D is equal to n times j. And now we can try kind of what we were doing before. Yeah, again, let's just follow our pencil. A minus B times C minus D. Well, we can write that out. That's going to be AC, okay, minus BC. We're just doing foiling, right? So AC minus B times C minus A times D, and then plus B times D. Okay, we wrote out that whole mess. And we know that multiplying these two things is the same as multiplying what they mean, which is nk times nj. And once again, we might get confused of like, what are we even trying to prove in the first place? If you ever get to a point where you're like, well, what am I trying to prove in the first place? Go back and say what we want to show, right? We want to show this. What does this mean definitionally? Well, it depends on which definition we're choosing, but we can say n divides this side minus this side, AC minus BD. That's what we want to show. And now we go back over here, and it seems like we're getting pretty close. We have AC right there. Oof. And then we have plus BD. So again, we could try to massage this. We could keep working with it and keep doing it. But I think one thing to say here is sometimes you just have to take a pass at a problem and see what you can get. And sometimes you run into something and it's not working, and you have to just say, OK, I'm going to step away from it for the day and come back later. And we might have to do that here. So I'll tell you right now, you could try to keep chasing this down. I don't know how to get rid of this BD when what we want is a negative BD. This is the claim we're trying to prove. So sometimes you just have to keep approaching it different ways. Yeah. So what we have is this right here. Where can we go from here is a different approach. Instead of just multiplying A minus B times C minus D. And this isn't something you would see offhand. This is one of those things. You'd have to approach it multiple ways and see if you could come to it. Is, well, the people can't see on that side of the board. OK. So A minus B is equal to n times k is the same thing as A is equal to n times k plus B. And we know that C is equal to nj plus D. That's just from, we'll bring the camera over here for a moment. That's just from these two right here. Right? These two, I just add B on both sides, add D on both sides. And now, if we look at what A times C is, A times C is equal to nk plus B times nj plus D. Let's FOIL. Let's see. nk times nj, that's going to be n squared kj. Fine. Nk times d is nkd. I'm going to break this up a little bit. And then we have b times nj is njb. And lastly, we have b times d. That's just foiling this thing out. Nothing special there, just foiling it out. Why does this look a little bit more useful to us? You might have to stare at it a little bit. Yeah?
We can factor out n from the entire right side, and then everything on the inside's in it belongs to the integers.
Great. So we have n showing up in each term except BD. And if we subtract BD on both sides, now we have AC minus BD. That's exactly what we wanted, AC minus BD. We want AC minus BD being a multiple of n. So AC minus BD is going to be n times this whole mess, which is, if I factor out a k, or an n, I get, and these aren't so important. What these things are KD, JB. The main point is this whole thing has to be an integer. Right? All these things are integers, so this has to be an integer. What we just showed is that AC minus BD is a multiple of n. That's the proof, because that's exactly what we wanted to show. So some proofs, you have a big eureka moment. Maybe with graphs sometimes you see like, oh, there's the right picture, and then everything pops, and you see everything. Sometimes you have to follow your pencil, keep playing with definitions. Sometimes you go down one rabbit hole, get stuck, you need to come back, go down a different definition rabbit hole until things come out. Yeah? I don't know. Is this proof in the notes was the question that was asked. I don't remember if this proof is in the notes. The proof itself isn't so enlightening. Like, I don't know if we learned too much from this other than that it's true. One thing we did learn is sometimes you do something perfectly reasonable. You play with the definitions and see if something pops out, and sometimes it doesn't pop out. And sometimes you just have to be like, OK, I need to come back to this a different day. And you use a different definition or play with the definitions a little different, and you do find your way. But the proof itself isn't so important. What is important is what this says. And let's remember what this says, because this is a lot of jargon. This says, if we go back to our problem, 57 times 26, what did we do? Mod 8? This problem becomes a whole lot easier. One thing I could do is do 57 times 26 and have to do all that long multiplication. A different thing is kind of like someone was saying, here's mod 8. One thing we could do instead is do 57 mod 8 times 26 mod 8. That's what number 2 is saying. Right? That like, if we can do them individually instead of together. So what's 57 mod 8? 1. That's just 1. Why? Because 8 times 7 is 56, which is just a remainder of 1 to get to 7, 57. What's 26 mod 8? That's the same as 2. Why? Because 26 is equal to 8 times 3, which is 24, plus 2. So now, what's this whole thing? 57 times 26.
2.
That's just equal to 2 mod 8. And that's what this is saying, right? This is saying that if you have two big numbers, make them small first. Right? Why? Because 57 is the same as 1. 26 is the same as 2. So use those instead. 57 is the same as 1. 27 is the same as 2. Use those instead. This gives us free license to any time we come across numbers, we can use. The point is that this is mod 7, not mod 8. But where's my eraser? There it is. If I want to do 71 times 79 mod 7, what do I want to replace 71 with? What do I want to place 79 with?
2.
Right. Why? Because 71 is in the same thing as 1. 79 is in the same class as 2. So really, what this clock looks like is you get all these things that are called equivalence classes. Sometimes they're called equivalence classes. Sometimes they're called congruence classes. You also might hear them called residue classes. There's a whole bunch of names for them. It's basically once you divide by something, what's the remainder? Sometimes remainder is called residue. But in any case, there's all these things, and it doesn't matter which you use. 1 is the same as 8, is the same as 15, is the same as 71, because the number line wraps. And because the number line wraps, you can use any one of them you want when you're dealing with one of them. So one way to say this is that These are the set of things that are congruent to 1 mod 7. These are the set of things that are congruent to 2 mod 7, and so on. So this is going to what a lot of people did ask earlier, which is, well, can you use mod before you multiply? Where does it show up? It means anything in the equivalence class you can replace willy-nilly, really. Great. OK. Yeah. So yeah, let's actually celebrate real quick, because this is a neat one. I have a question, and that is, does 9 divide 82710? This is some integer. Does 9 evenly divide it? Who thinks yeah? OK. Can someone tell me why they know that 9 divides this? Yeah.
The digits sum to something that's divisible by 9.
So the digits sum to something divisible by 9. We may have seen this trick before. It was actually in the notes back when we were proving things about numbers in like the first few lectures. And we have 8 plus 2 plus 7 plus 1 plus 0. That's 8 plus 1 is 9, 2 plus 7 is 9, so really that's 18. And 9 divides 18. So this is divisible by 9. And we kind of proved this through some way that wasn't that enlightening before. Let's take a look at this again through the lens of modular arithmetic. This is really the power of math, is you get more and more lenses and you can learn more. You can say things much easier as you go along. So, really, when we say 9 divides this, what we're saying is 82710 is congruent to 0 mod 9. That is, there's no remainder when you divide by 9. And how can we see this? Well, what is 82710? That is equal to, well, 8 is in the what? 10,000s place. So that's 8 times 10 to the 4 plus 2 times 10 to the 3 plus 7 times 10 to the 2 plus 1 times 10 to the 1 plus 0 times 1. Right. That's what a positional number means. It means we can break it out into the 10,000s place, the thousands place, the hundreds place, the tens place, the zeros place. And if I want to know what this is mod 9, what's special about this? So for example, we have 8 here, 10 to the 4. What's 10 to the 4 mod 9? I'm hearing some ones. Can someone tell me why 10 to the 4 is 1? That's kind of a big number. How do we know that that's 1 mod 9? Yeah.
Whatever we prove from proof 2, that property tells us that 10 times 10, 10 is the same thing as 1 mod 9. And so 10 times 10 would also be 1 mod 9. Yeah. And then 1 mod 9 times 1 mod 9, which in this case would be 10 squared times 10 squared.
Yeah.
You get it.
Exactly. So 10 to the 4. 10, we know what 10 is mod 9. 10 is 1 mod 9, because 9 goes into 10 once with a remainder of 1. So really, 10 to the 4 is 1 to the 4. You might as well just replace 10 with 1. It's in the same congruence class as everything. If we drew a picture for the circle for 10, the clock for 10, or 9, sorry, for the mod for 9, if you looked at the equivalence classes, 10 would be in the same one as 1. So we can replace it there. 10 to the 3, that's just going to be 1 to the 3. 10 squared, that's going to be 1 squared. That'll be 1 to the 1, and so on. So really, if we're doing this mod 9, we don't need to add everything and do all the stuff to figure out whether 9 divides everything. We can do mod 9 through each of these as we go. That takes away all the 10s, turns them into 1s, and all we're doing is adding up the digits. 8 times 1 plus 2 times 1 plus 7 times 1 plus 1 times 1 plus 0 times 1. This is, like we may have memorized this. Early in class, we kind of proved this. But this is why adding up the digits y if 9 divides the digits added up is 1. So another thing you proved on the homework was the question of whether 11 divides 5, 2, 9, 1, right? And it does for this really weird reason, right? And it's because 5 minus 2 plus 9 minus 1, that is 11 and is divisible by 11. This, you should remember this from homework 1. Yeah, homework 1, I think. This was one of the homework problems, and you did it for just 4 digits, but this is true no matter how many digits you have. Specifically, why does this work? Well, it's 5 times 10 to the, 3, plus 2 times 10 squared, plus 9 times 10 to the 1, plus 1 times 10 to the 0. What's 10 mod 11?
Negative 1.
10 mod 11 is negative 1. We'll need to talk about negative numbers more in just a moment. But if we drew the circle and we, we're out of room. If we drew the circle for 11, we'd have 0, 1, all the way around to 10. Going back, negative 1 gets us to 10. Right? That's our negative 1 is 10. So 10 being negative 1, this is going to be negative 1 cubed. Oh, my goodness. Negative 1, let me write this better. Negative 1 cubed. This would be negative 1 squared. This would be negative 1, and so on. So really, negative 1 squared, just 1. Negative 1 times itself is 1. Negative 1 cubed is going to be negative 1. Right? So in general, negative 1 to the k is going to be, if k is even, what will this be? Negative 1 to an even number. Yeah. So that'll just be 1 if k is even. What if it's odd?
Negative 1.
Yeah. So if this is an odd number, that is, it's 2j plus 1, that'll be negative 1 to the 2j times negative 1. This would be 1, because it's an even, and then we'd be left with negative 1. So really, this is why the alternating series works. You proved it, so that's another reason it works, but this one's kind of enlightening almost. Right? Like this one, you could see that no matter how many digits we have, it's always going to be 10 to some power, which is going to be negative 1 to some power. And that just changes negative and positive because 3, 2, 1, these are going to be even and odd changing. So I think we just, want to take a moment to appreciate that now that we have modular arithmetic as a lens, we can say much more powerful things, or say things that we were able to say before, but in a much easier way. And we've known since grade school that 7, 9, 3, 5, 1, divisible by 2?
No.
Why? Because the last digit, right? That's all we know is the last digit is not divisible by 2. We've always done this sort of thing of like, oh, the last digit, that's divisible by 2, that one's not. Why is that true? Yeah.
Well, I had a question about the 11.
Okay, uh-huh.
Because we did 5 times negative 1 to the third, wouldn't it end up being negative 5?
Yes, exactly. So, I see. 1, 9, 2, 5. Let's see, did I do that wrong? That's negative 1. Yeah, I think I did those wrong. Something like that, I think, would be right. Okay. Yeah. Mm-hmm.
Also, how did we get negative 1s? Is that supposed to be 10 mod 11 is negative 1?
Yes, 10 mod 11 is negative 1, exactly. Yeah, we haven't talked about negative. Yeah.
So does all this mean that 1 plus 1 is 11?
1 plus 1 is 11 mod 9. Well, let's see. 1 plus 1 mod 9. Well, that's going to be 2. And the question is 2 the same as 11 mod 9? Sure is. 2 and 11 are the same mod 9 because 9 goes in, or 9 goes into 11 once with 2 left over. Great. Right, so this is something we just memorized from grade school. We've never known why it's true. I've never known why it's true before this, right? Like, we just kind of memorize whether 2 divides something by looking at the last digit and seeing if it divides that. But if we break this up now, 8, 5, 3, 2, like break that number up, that's going to be 8 times 10 cubed plus 5 times 10 squared plus 3 times 10 to the 1 plus 2 times 1. Using what we just proved, instead of doing mod 2, because that's really what we're asking. Does 2 divide it? We want to say mod 2, does this equal to 0? Right? That there's no remainder when you divide by 2. Instead of looking at this whole number and doing mod 2, what's this mod 2?
0.
It's going to be 0. Why? 10 is going to be 0 mod 2. 10's always 0 mod 2 because 2 divides 10. Same with this 10, that's going to be 0. Same with this 10. So no matter what digits you have past there, mod 2, all these are just going to go away to 0, and all we're left with is the ones place. So this is a grade school thing you memorized. Whether a number is divisible by 2 or not, that's why. Like, we may have never seen before why it's true, and now we do, because we have modular arithmetic. OK, so let's actually, I want to give you one thing real quick so you're not left struggling with it on homework. And then we'll need to talk about negative numbers and something even a little scarier. All right, so first off, I wrote something scary on the board that we didn't touch, which is 5 to the 58 mod 7. And I said, what's that? And already, we're off a little bit better. Because instead of doing 5 to the 58, I could do, I can start breaking it up into 5 times 5 times 5 times 5, and group these, and then start making the numbers smaller as I go, so I don't have to deal with really big numbers. Basically, make them small each time because I can always deal with smaller numbers by putting them into the residue class. OK, but this is still a bit gnarly. If I wanted to do it all one by one, that's a lot. So one thing to note, and this is just going to be relevant for your homework, so let's look at it. 5 to the 58, that's the same thing as 5 times 2 to the, 29? 2 times 29 is 58. And what that means is I have 5 squared to the 29. 5 squared is 25. And now it's going to start getting nasty if I keep going. What would be a good step to do here before I continue forward? Yeah. Mod 7. 25 mod 7 is what? 4, yeah. Why? Because 25 is equal to 3 times 7 is 21 plus 4. Right? There's a remainder of 4. So that's 4. So instead of doing 25 to the 29, that's nasty, we'll do 4 to the 29. And really, I should be putting that there, congruent. So 4 to the 29, that 7. So 4 to the 29. Well, again, I can break that up into 29 is still big, but we've done a lot better, right? We went from 58 to 29. We halved it. Now, we can't have 29 again because it's odd. But we can break it out into 4 is 2 times, let's see, 14 plus 1. 2 times 14 is 28 plus 1. So one way to say that is break off this plus 1. That's going to be 4 times 4 to the 2 to the 14. So any questions about this step right here? All I did is say that 4 to the 2 times 14 is still right there. And then this 4 to the 1, I just bring it out front. Yeah?
So are we getting to like there some sort of rule where it's broken down by cases, like odd and even?
Yeah, so we are breaking it up by odd and even. What this is called, and it'll be in the notes, this is in the notes, this is called repeated squaring. So instead of dealing with 58, you can just divide it by 2 each time and go much quicker. Because if you divide 58 by 2 repeatedly, you get there quickly. You know, we won't get into it, but we only have log base 2 of 58 steps to go. Log is great for us because we're dividing by 2. Log is just saying how many times you have to divide by 2 until 58 goes down to 1. So, right, now we have 4 squared, which is 4 times 16 to the 14. Again, let's make our life simpler. 16 mod 7 is, right? 16 mod 7 is going to be 2. 7 times 2 is 14. 2 left over. Great. So now we can do 4 times 2 to the 14. And this is still nasty, but so much better than trying to do 5 to the 58. Just, brute force. OK. So again, we can just keep breaking this up. 4 times 2 to the 2 times 7. Right? I just split this up. I divide it by 2 again. And we get 2 times 7. And what that gets us is 4 times 4 to the 7, which one way we could say 7 is 2 times 3 plus 1, which means we get another 4 over here. So this is going a little fast, but the main thing we want to see is what the repeated squaring algorithm looks like. The notes give you a recursive algorithm. You could do that fine, too, but this one feels a lot more direct to me. It's doing the same thing. So we're just kind of breaking them off one by one. So 4 squared is 16. Again, we already know what 16 mod 7 is. That'll be 2. So that'll be 2. 4 squared is 16, so we have another 2 in there. So now we have 2 times 2 cubed. 2 cubed is 8, which is what mod 7? So congruent to 1, mod 7. And that gives us 2 times 1 equals 1. Oh, no, equals 2. So that's the whole process. 5 to the 58 mod 7 is 2. Little bit of a long process, but all it's saying is you start with 5, you multiply by 5, and it just goes round and round and around. And instead of growing bigger and bigger, we can just kind of slap it down to the small 0 through 6 thing as we go. We have 12 minutes, so let's talk about multiplication and addition, what a lot of people have been wondering about for a while, which is negative numbers. Yeah, let's erase all that. All right. Thank you. So we're going to retrain our brain of what a negative number is. We've gotten used to negative numbers just existing. Throughout history, that's been kind of contentious, actually. Negative things don't exist. I can count chickens, 1, 2, 3, 4, 5. There's no such thing as 0 chickens. You can't have a nothing of something. And they also were really upset about negative numbers. People throughout history have not always been on board with 0 being a thing, and especially negative numbers being a thing, because you can't count them. They're kind of a conceptual mismatch of what we have. But what we really want to say is what we've always been dealing with is something called an additive inverse, and that's going to look a little bit different here. Here's the definition. we looked at it as going backwards around the clock. We're going to look at a different way to look at negative numbers here instead of going backwards. And x is additive inverse, is additive inverse of a mod n. And what that means is named negative a, but that's just a symbol. Negative a is just a symbol. We're going to call x negative a if, x plus a is congruent to 0 mod n. Something is the additive inverse of a is if you add it. Something is the additive inverse if when you add it, you get 0. That's all it means. It's whatever you add to a to get 0. Before, that didn't exist. If you have the natural numbers, 1, 2, 3, 4, 5, there's nothing to add to 3 to get to 0, unless you invent the integers and say, well, now there is. I'm going to add, I just invented this and put a little symbol in front of it and say, this is a thing that when I add to 3, I get to 0. That's kind of an invention, though. That's a weird thing to swallow, but that's kind of an invention, to say there is a thing to add to 3 to get to 0. Not everyone throughout history was happy with that. Here, though, what's the additive inverse of 3? What do I add to 3 to get to 0? 3 plus 4 is 7, which is 0 mod 7. So what are the negative numbers? It's, negative 3 mod 7 is going to be 4 because 4 plus 3 is equal to 0 mod 7. 4 is the thing that when you add it to 4 is the thing that when you add to 3 gets you to 0. So if you add 3 to something, the way to undo it is to add 4, because instead of needing to go backwards, the trick about a clock arithmetic is you don't have to go backwards to get back to 0. You can just kind of keep going forward until you get to 0. And this really brings us to something a little bit even weirder here, which, what's our time looking like? Perfect. Yeah. Because what I want to say here then is, what's 3 times, let's say 3x is congruent to 2 mod 7. What's x? Usually, I'd say, well, let's multiply this by 1/3 on both sides. And now we get x is equal to 2/3. But what's 1/3? That's 0.33333, like that doesn't exist with what we're dealing with. We don't like 1/3. So we're going to define something called the multiplicative inverse. Multiplicative inverse. And what that is kind of the same, is x is multiplicative inverse, multinv, of a, and that's going to be mod n. And what we call that thing, it's named a to the negative 1. That's kind of what we think of like with 3 to the negative 1 or the sort, a to the negative 1. If x times a, what do you think is going to be on this side? 0. OK. I'm hearing some things. There's 0 and there's 1. In this case, it'll be 1. And 0 and 1 are kind of the most important numbers around, or some of the most important numbers around. Why? Because this is special for addition. 1 is special for multiplication. Right? So like if a does something, if I multiply something by 3, if I say, I have 5 and I multiply by 3 mod 7, I've done something to 5. I've multiplied it by 3, and it sends it to some other number. The multiplicative inverse is the thing that undoes that. Right? 1 is the thing that's neutral for multiplication. 0 is the thing that's neutral for addition. Right? So these are very special numbers. And what this is saying is that x is a multiplicative inverse if it's the thing that when you multiply by a gets you to 1. Right? It's the thing that undoes whatever you did. So what did I just write up there a moment ago? I said, what is 3x? Let's say 3x is congruent to 2, and we want to solve for x. First off, we need to know what 3 inverse is, mod 7. What's the thing you multiply 3 by to get 1? What was that?
5.
5, is that true? So, we kind of have to look. We want to get 1, so we can look in its equivalence class and see what things will get us there. And yeah, 15 is the closest thing to a multiple of 7 that we might want. So yeah, that's going to be congruent to 5. Why? Because 3 times 5 is equal to 15, which is congruent to 1 mod 7. So this is where things get really weird, right? Before, we had the number line. We had 1, 2, 3, 4, forever. We had 0. And then we said, well, what if we want to undo addition? We have to invent the negative numbers and say, like, OK, now the integers exist. And we go backwards. And then we say, OK, what if I multiply by 3? How do I undo that? And this is where the rational numbers come from. People said, well, OK, we want something that means the opposite of multiplying by 3. The weird thing about clock arithmetic is you don't need to invent new number systems to have a multiplicative inverse or an additive inverse. It's all right here. So 3, you don't need a 1/3. 1/3 is just 5. 3 times 5 is 1. Again, college math gets weird. 3 times 5 is 1. You have to add mod 7. But this is modular arithmetic. 3 times 5 is 1. That means they are multiplicative inverses of each other. Yeah? Yes. So 5 is 1/3 in the sense that it is the multiplicative inverse of 3. So we have the number 3, and we're asking, what is x so that x times 3 is equal to 1? And it's not obvious what thing you multiply 3 by to get 1, mod 7. But if you look, there's not too many numbers right here. 3 and 5 are going to be multiplicative inverses of each other. That is, 3 times 5 is 15, which is 1. Yeah. So it's pretty definitional. It's not like there's a magic, well, 1/3 is 5. It's look at the number system and see what number you can multiply it 3 by to get 1. That's the multiplicative inverse. We're almost done here, so I'll just ask a couple more questions. I want to ask, let's just categorize 7. So 3 inverse, we saw, is 5. What's 2 inverse? What do I multiply 2 by to get 1?
4.
I'm saying 4, great. Because 2 times 4 is 8, which is 1. What else do we have? What's 6 inverse? What can I multiply 6 by to get 1? Yeah? Can you say that again? 3x is congruent to 2. Yeah, we never solved this. Great. So if we want to solve this, I can multiply 3 inverse on both sides. What's 3 inverse again? 5. We know 3 inverse is 5. So these would cancel. But now on this side, we would have x is congruent to 2 times 5, which is 10, which mod 7 is 3. So really, what we've just solved for is x. So we say x is equal to 3. Let's plug it back in. Let's see. 3 times 3 is 9, which is congruent to 2 mod 7. We did solve it correctly. we're able to cancel. By having multiplicative inverses, we can do algebra. We can cancel on sides by multiplying by the multiplicative inverse on both sides. This is what that gives us. And we have more to say, but we can say that next time. We're out of time. Yeah. Yeah.
It's 6, multiplicative inverse
Ooh.
is 6.
6 times 6 is 36,
Oh yeah, 36.
which is mod 1 when you're looking at 7, because 7 times 5 is 35. Exactly.
I have a question.
Uh-huh.
I feel like